Hi, welcome to Munro Live. I'm Paul Turnbull. Today we're going to talk a little bit about inverters. I did promise that I would do an inverter video, and so I'm going to try to follow through on that. Here we have the Tesla Cybertruck inverter. I want to show you, what it looks like when it's all put together. This bolts right onto the side of the motor, and these three connections drive the three-phase motor. And it has the DC connection going into the back. So what an inverter does is it turns the DC from the battery, DC electricity, direct current, into alternating current that the motor needs to produce rotation and torque. And I'm, saying that is one thing. It ends up being kind of magic. The control board, here's the computer. It controls the switches that are inside this in order to turn that DC into AC. But saying those things really doesn't tell you how it works. And for an engineer, we kind of need to know how it works and not just what it does. So again, here, this one is from the Model Y. It's sort of taken apart. There's the control board. And one of the things I wanted to point out on the control board is that there's this low circuit and this high circuit, which refers to the low side of the battery or negative pole, and the high side of the battery. So this is the DC low and high connecting to all the switches. And then there are these 6 gate drivers and the 6 identical circuits that drive the switches and tell them to turn on and off. And they also have this A, C, and B. So this is a collection of switches that are all connected to the one phase, the A phase. These are all connected to the C phase, and these are connected to the B phase. So again, this is sort of the same thing, but here we're seeing the switches. In this case, the switches are done with discrete components. These are MOSFET switches. They're all transistors. So it's a kind of solid-state switch. In this group, there's a group of 4 switches that are all connected together and switch at the same time. And then another group of 4 and another group of 4 for a total of 6 groups of switches. And then there's this big capacitor. This capacitor helps store energy because the things are happening here so fast that the battery cannot accept the energy at that rate of speed. And so we need the capacitor to smooth things out so that the energy to and from the battery is at a rate that the battery can accept it. So if we look inside of these switches, we'll see something like this, integrated circuits that are mounted on a copper plate so that the heat can get from the switches to the heat sink underneath. And we flow coolant through this array of fins to help cool the switches. And why do you need to cool them? Because through these tiny integrated circuits, we're going to put hundreds of amps of current. And the hundreds of amps of current produces some heat because there's a small amount of resistance as you go through the switch. There's also a small amount of energy that's used to flip the switch. And so they call that switching loss. And so the combination of the conduction loss and the switching loss produces a little bit of heat. And we have to get rid of that heat or manage it because we're continuing to make things smaller. You can see this was the Model Y, and then the Cybertruck, which actually is twice the voltage and the same current, so more power, but a smaller package. So we continue to make the package size of these things smaller and smaller, and that drives the heat to having to do real serious engineering on the thermal side. even though these things are very nearly 99% efficient and they're at their peak, 97% efficient even when they're operating at relatively low efficiency operating points. So these things are amazingly efficient. The power coming in the form of direct current and the power going out in the form of alternating current. So all that's great. So now you know what it does, but how does it do it? And so I put together a little science project to be able to show you how it's done. I went looking on the internet for how these things work, and most of the videos that are out there, they immediately go into circuit diagrams and start talking in jargon that is fine for electrical engineers, but I couldn't find anything that was at a higher level and making so that someone could really see how it works. So I decided to go ahead and build one. So this is an inverter. There are 6 switches. It's going to be a hand-driven inverter, so I'm going to perform the function of the control board. The inverter, the 6 switches, these 2 switches are connected together and then also connected to the top side, the high side of the power supply. The power supply is set at 1.5 volts. I could be using a D-cell battery, but instead I wanted to use a power supply just so you can see the values. All these switches are connected together at the top, and then at the bottom, they are connected. This one is connected to this coil. So these 2 switches are connected to this coil. These 2 switches are connected to this coil. And these 2 switches are connected to this coil. And these coils are held together with twisty ties, and I've got a compass in the middle to show you the direction of the magnetic field. And it's all taped down with Scotch tape onto a piece of scrap flooring. All right, so I've seen 2nd grade science projects that have better build quality, but if we can just get past the janky setup, I think we'll be able to see how these inverters work. So the way that it works is we close these switches. So we have DC power coming in, and we close these switches. I can close one. Now, if I close this switch here, then the DC power will shoot straight through and go straight here. So that's a dead short back to the power supply. This would be a bad thing. If you do that with an 800 volt system on a battery that can deliver thousands of amps, then your switches turn into smoke very quickly, and then you have lengthy meetings about how you're never going to do that again. So we don't turn both switches on. We either have this switch on or we have this switch on, never both. So we set it up so that we can't have both switches on at the same time. If we have this switch connected, we'll label that as a 0 because it's connected to ground. If we have this switch connected, we'll label that as a 1 because we have it connected to the high side. So this switch is now in the 1 position. And then I can close these 2, and then that gives a circuit so that the electricity goes in here, goes through the coil. All the coils are connected together here in what's called a Y connection. So the electricity goes, 100% electricity goes into this coil, then it goes to the Y connection, and then 50% of the electricity goes out through each of these 2 coils and back to the power supply. All right? So I'm going to actually graph and plot what is happening with the current. So when we have things set up here, with 1, 0, 0. So we'll say this is 1, 0, 0. Then we have the current going into A phase. 100% of the current is going into the A phase. And then 50% of the current is coming out of the B and the C phase. So we've got B and C. If we'll call current going in positive and current coming out negative. So I've got 100% of the current going in the A phase, 50% of the current coming out of each of the B and the C phases. Okay, so when we do that, we've got the magnetic field is aligned directly with that A phase, and we got the compass needle pointing it up. So now if I want to make things turn, I want to rotate the compass needle, I'm going to open one switch and then close another. Now, 100% of the current is leaving the C phase, and so the south pole is now pointed at the C phase. And 50% of the current is going in each of the A and the B phases. I only had to switch one of the pairs of switches, change the state of one. I didn't have to touch these two. And I moved the magnetic field from this direction. Now it's over to this direction. So again, I've got 50% of the current going into the A phase, and 50% going into the B phase, B coil. Why I'm calling them phases, we'll talk about that in a little bit. They're just coils, but I'm calling them phases. And then 100% of the current is coming out of the C coil. Okay, so that's the second part. There's a total of 6 of these, so bear with me here. So the next set here is, by the way, that was, this was 1, 1, 0. Now I've got 0, 1, 0. So 0, 1, 0 is the setup for the switches. And I've now moved the magnetic field so that it has rotated again to the north is pointed directly at the B phase, the B coil here. So 100% is going into the B phase. I'm using the word phase and coil interchangeably, and we'll see why in a little bit. And then 50% of the current is coming out of each of the A and the C phases. So I've got A and C. Okay. Now to the next position. Now I've got the south pole is aimed up at phase A. 100% of the current is leaving from phase A. And the north pole of the compass is now halfway between the B and the C phase. So this is, again, 0, 1, 1. That's how I've got the switches set up. And that gives me 180 degrees now of rotation on the 180 degrees of rotation on the rotor. So I'm using the compass as a motor rotor. Okay, so I'm going to plot this again. The 50% in the B and C, and 100% coming out of the A. So we've got A, 100% coming out, negative, and then B and C, 50% going in. Halfway there? Okay. Now, open this one and close this one. Again, only changing the state of one pair of switches, leaving the other two switches alone. And it has moved now so that the north pole of the compass is pointed towards the B phase, the C phase, which is where all the current is going in. So we have the C phase has all the current, 100%. And then the A and B phases have 50% of the current coming out. Okay. Now we close this one. We have 50% of the current going in A and C, and 100% of the current coming out of B, so the south pole of the magnet aligns with the B phase. So 100% of the current is coming out the B phase, and 50% of the current is going in from the A and the C phases. And then the last one, just back to where we started, which is, open this and close that, and we're back to where we started with, I forgot to put down you get the idea though, we got different ways of assigning the states. We end up with A back at the top, and B and C at 50%. So I could operate a motor just like this, but just by slamming the switches home. There are 6 different steps of this arrangement, and so we call this kind of control, it's one example of 6-step control, but we can do better. So we're able to sort of click it from one step to the next. And if I did this then, and put the current in 100% and then switched it just as the needle, just before the needle arrives perfectly aligned, then I could get smooth rotation. But it would still be a little bit jerky because the current is jumping from one coil to the next. So we'd like to have nice smooth transitions from one coil to the next. There is a way we can do that. So let me show you what that trick is. We call that, we're just going to turn I'm going to turn the switches on and off really fast. I can't do it by hand, but we'll show you. So if I go here and there, that's the next switch. But I can go back and forth really fast and get something that's halfway in between. So if I switch the switches really fast, on average, it's half over here, half over here. I can get something that looks halfway in between. We call that switching the switches really fast. We call that pulse width modulation. So you're just turning the switch on and off really fast. This would be, sometimes we do this about 10,000 times per second. So this would be 100 microseconds. And so if we turn it on and spend half of the time on and half of the time off, we call that a 50% duty cycle. And that will, as we turn it on, the voltage immediately changes. And that causes the current to start to rise. So why doesn't the current immediately rise and go up to the higher value? And that's because the rising current in the coil produces a magnetic field. And a changing magnetic field, as the current is rising, produces a voltage in the coil which fights against the voltage from the power supply. And so the current isn't able to rise immediately because it has to fight against this voltage that's generated in the coil. So it rises slowly, and then just as it gets to this point, we turn it off. And why doesn't the current immediately drop? It's now suddenly an open circuit. And so how does the current continue to flow even though I've opened the circuit? And the answer is because that same thing, as the current starts to drop, the magnetic field from the coil collapses. And that's a change in the magnetic field, and the changing magnetic field generates a voltage, and that voltage that's generated by the coil keeps the current moving. And so the current keeps going, but it does start to drop off. And then we turn it back on and turn it off, turn it on, turn it off, and we end up with an average current that is equal to half of what it would be if we just had left the switches on continuously. And so we can choose when we turn the switch on and off. If we turn it off right away, we might have a 1% duty cycle. If we wait and turn it off right at the last second, we might have a 90% duty cycle or 95. And so we can choose anything in between. We could even smoothly ramp from 1% to 100% as we do this. And that smoothly creates a ramp of current between this switch position and this switch position. So by PWMing, we can fill in all of the positions between this position and that position. And so if I go back to my graph, and I look at A, if I use PWM, the current in A will change smoothly and go from this point to that point, then change smoothly again from this point to this point, and again here. And we end up with something that looks pretty close to a sine wave. And the same thing happens with C, the C coil. And the B coil. And we end up with 3 sine waves, or something very close to a sine wave. And each sine wave is shifted by 120 degrees. So the B phase is at 120 degrees, looks exactly like the A phase. And the C phase is exactly like the A phase, but shifted 240 degrees. And since they're shifted in time, we call that each coil has the same current in it, shifted in time. We call that a phase shift. And that's why Charles Steinmetz, when he first figured this out in the 1880s, called these different phases. So it's AC current, 3 phases, each one shifted by 120 degrees, and that produces smooth rotation. And the magnetic field smoothly rotates with just 3 coils. I get a smoothly rotating magnetic field that will drive this compass needle round and round. So that is how we control electric motors, how we produce 3-phase AC with 6 switches to turn a compass needle or a motor and to make it rotate around. The way we do that is to always turn the switches on just before, in advance of the needle lining up perfectly. So just before it lines up with the next pole, we turn on the next switch, and so it moves on to the next one and on around the circle. So always when we're motoring, always turning on the switches a little bit in advance of when the compass needle is pointed perfectly at the phase. So every time I do these videos and I tell people about how motors work, I get questions about, hey, what about regen or recuperation or generation? We know that these same motors also do regen. So how do I control it for regen? And that's the beauty of this, is it's almost exactly the same thing. Only instead of turning on the switches just before the compass needle gets aligned with the switches, we wait and we turn on the switches just after the compass needle has passed. So something else is driving the compass needle, something else is driving the rotor. And as we drive the rotor past the magnetic field, then we do the switching. And that produces a drag torque. It's a little bit like spark advance in an internal combustion engine. So normally you would fire the piston just after it reaches top dead center, and that pushes the piston down and you get motor. But if you wanted to produce an engine drag torque, you could fire the piston just a little before top dead center, and that would produce a drag torque. And that's kind of what we're doing with turning the switches on a little bit after the magnetic field. So the magnetic field is constantly producing a drag on the rotor as it's going around. So that's how this operates as a generator. There is a little bit more to it though. So yes, we turn on the switches as the rotor has passed the magnetic field. But, so if the motor is spinning fast enough, then the changing magnetic field produces a voltage that's higher than the battery voltage, and the current will flow back to the battery. It would be nice if we had a switch that would kind of automatically, as soon as the voltage is higher than the battery voltage, allow conduction back into the battery. And in fact, that's what we have. We put, in addition to these switches, we put a little diode, actually a pretty big diode, between the positive and negative. And the diode is what a diode is it is like a one-way switch. It doesn't allow current to flow this way through the switch, but it does allow current to go this way through a switch. And so if something should happen here with the motor, where the voltage from the coil is higher than the battery voltage, the current will immediately begin to conduct back up through the diode and charge the battery. So if the motor is spinning fast enough, then it will charge through the diodes back to the battery, and the diodes sort of automatically turn on at exactly the right moment to allow that conduction for each of the phases. What if the motor is not spinning fast enough and the voltage from the motor is too low to charge the battery? So we want to regen all the way down to the stop. So as we're coming to a stop, we need to collect that kinetic energy, turn it into electricity, and store it in the battery. So if the voltage from the coils is too low to punch through that diode and charge the battery, what do? Well, we can use that PWM trick where we turn the switches on and off really quick. And every time we open the switch, the collapsing magnetic field from the coil, now the coil is, that collapsing magnetic field is happening very fast, much faster than the rotor is spinning. And that produces a very brief spike in voltage. And that spike in voltage is higher than the battery voltage and drives the current back through the diode and charges the battery. But it's so quick, it's in such a short pulse that the battery cannot accept that charge at such a high rate. And that's why we use a capacitor. So we have a big old capacitor. A capacitor is able to accept that charge, that super brief moment, just as you open the switch where the voltage spikes. And using the collapsing magnetic field of the coil to generate this little brief spike of current, and it's stored in the capacitor. And then over time, the capacitor sends that power back to the battery, or in this case, the power supply. So that is how we're able to do this charging regen even at very low speeds when the voltage from the motor is lower than the battery voltage. We use PWM to turn the inductance. Inductance is the rate of magnetic field, the amount of magnetic field you get per amp in the coil. So the inductance of the coil and the switching here produces a boost converter that boosts the voltage up to the battery voltage, and we store that energy in the capacitor so that it can be very smoothly generated out to the battery. So motoring, generating, you can go forward or backwards just by changing the order that you turn the switches on and off. Forward, backwards, motoring, generating, all from controlling 6 switches. So this is how inverters work. It's why they call them motor controllers, because this is controlling that motor. And also why it's called speed controllers in hobbies, at the hobby level. So we've got a very simple circuit that was sort of easy to demonstrate, and even at a second grade science project level, you can get an incredibly deep understanding of how electric motors work. And so that's all we have for you today here at Munro Live. Thanks for tuning in. I really appreciate you guys. And it was a tricky question when you asked it. I'm glad I was able to answer. Thanks a lot. Bye-bye.